to kick off the workshop, we're going to have a Google Keynote talk by 3 amazing speakers, Dan, Brendan, and Kallista. And they're going to tell us about the state of the art in federated aggregations and privacy. So Dan, the floor is yours.
Thank you. Welcome, everybody. I wanted to take a minute to just talk about the history of where we've been in this space for the last few years. First blog post on federated learning, I think where the term got more widely introduced to the non-academic audience was in 2017. And in the years since, we've been working to bring these technologies, make them more mature and bring them to production in more cases, including with federated analytics and into areas like Android's private compute services and other aspects of Google's apps and services. So this has been an example, I think, of where research done at Google, as well as really influenced a lot by the community, has had an impact on the way Google's products and services are built. So we always kind of have to start a little bit with just why is Google interested in this space at all? You know, the original motivation and what continues to be our motivation today, it really is driven by the value proposition that we see both for users and for the engineers who are building the products and services that those users enjoy. And so for users, we want to be able to offer them a better privacy trade-off than what they might get otherwise for at a given quality of apps and services, but also to make those apps and services better and to reduce their risk exposure just in general from having from a data minimization perspective. For the engineer, there has to be kind of a comparable value proposition because Google product engineers are trying to make things that work well for people. And the value proposition for them is access to better data than what they might have had access to if otherwise, right? Because Google won't log certain kinds of sensitive information, as well as having higher privacy standards overall, being able to meet rising privacy standards when we build apps and services. And so there's really, when an engineer is thinking about making a product better, there are really kind of 2 main flavors. And we think of these as federated learning and analytics and in terms of the overall methodology of what people are trying to accomplish. From when an engineer is doing federated learning, they're trying to improve some feature, usually in an app, via machine learning. So the ML to make things better is a big part of the way apps are built today. And we want to enable that without having data needing to be centralized at Google and with privacy by default. Now, privacy, of course, isn't binary, nor is it like something that you either have or don't have. It's a spectrum, and it includes, there's different aspects to that. We'll hear a little bit later from Brendan about the data minimization and data anonymization perspectives on what we're doing with the federated learning technology stack we have here at Google. In the federated learning that we think about here really isn't just train a model. It's actually the full workflow that engineers need to do when they're making a product better, right? So that involves often many different models or to do grid searches to find out if those models are working better than what came before. That latter category really opened the door to us for the need for federated analytics, which is basically around the data science questions that an engineer needs to ask or a product needs to ask in order to figure out how well an app is working. Just training a single model isn't really enough. We need to be able to make decisions about how things get better based on how users are interacting with the features in that app. And the demand there has actually, within Google, been pretty large because a lot of times apps were kind of, still are sometimes flying blind with respect to how users are interacting with those apps if the interactions involve sensitive data that can't be logged. So the system that needs to exist to power these things really is an iterative workflow, right? We're trying to enable that engineer to be able to interact with devices many times, as well as interacting with proxy data that is in the cloud. I'm not sure if you can, I think there's a gray cloud around that gray arrow on the right side that isn't showing through super clearly. The left half is decentralized and the right half is the centralized proxy data. And so enabling this workflow is really key for those engineers to be able to do their jobs. And over the last few years, this has been working pretty well. with respect to teams being able to use these things effectively. Android 12 has a bunch of machine learning features. Many of them are using federated learning or federated analytics by the engineering teams in order to work. Also, Google Software Keyboard uses federated learning for almost all the models that it trains, and software keyboards require lots of models in order to work. Otherwise, those tiny key targets just don't work very well for typing or anything else. It's also playing a growing role in other Google apps, which like Android Messages, which has been experimenting with federated learning technologies, and Google Health Studies, which was using federated analytics as one of the mechanisms for studies like this respiratory study with Boston Children's Hospital. So the kind of federated learning that we're talking about here, in the bigger focus for Google traditionally has been this cross-device federated learning setting. This was our first focus and continues to be where a lot of Google's interest lies. Of course, in the academic community, as well as in the health and financial spaces, the cross-silo federated learning setting is playing a growing role, where rather than data living on users' devices, it lives in silos. Like each hospital has their own medical records, and they work together to learn a centralized model. These two settings, I think, have been explored pretty well in the literature, including in the Advances in Open Problems and Federated Learning paper, which many of you actually are co-authors on, thank you, that came out of the version of this workshop we hosted in 2019 and was published in FTML this year. We've also noticed, though, a really interesting kind of middle section in the last year or two at Google, which we don't really have a good name for yet, but I just wanted to mention to you all. We're kind of thinking of this as the cross-user single controller federated learning setting. This is really about being able to provide the same kind of user-level privacy guarantees and that we do in cross-device federated learning on data that Google actually has, because it's data that about users that are logged in and using a Google service where the primary copy lives in the cloud. Sometimes that data actually has policy or compliance reasons to be processed in a particular location, say to stay in the country that it came from, for example. And so we're really interested in being able to have machine learning frameworks that honor those policy constraints on data locality and also offer the same privacy guarantees we get in cross-device FL. And so your input on the name here would be great. This is a little bit different than just saying differential privacy for training a centralized model, because we still have that data processing locality guarantee, but some of the considerations that we have in cross-device or cross-silo federated learning are actually a little different. And here's kind of like maybe the one-line, the two-line summary. The unit of privacy that we care about in cross-device and this cross-user is user from a differential privacy perspective. But the centralization versus properties look different across these three. So that might be a fun topic for possibly a breakout session if anyone is interested in brainstorming a little bit about that one. So in terms of what it takes to build systems that do things like that, systems is going to be one of the themes we'll talk about today. I mean, over the course of this workshop. But there's very different system properties you need for cross-device federated runtimes versus data center runtimes under these two different kinds of regimes, multi-homed or policy-aware centralized. And those have different data minimization properties. We'll hear a little bit more from Kallista later today about some of the protocols that we use to make things safer in that cross-device setting. But what's common across these is that we really have the same learning and analytics questions we're trying to ask and answer in these domains. The algorithms for doing learning effectively look very similar, no matter which domain you're running here. Not completely, there are differences that will leak through, but largely. Same for analytics, we have similar algorithms and methodologies that we're interested in developing that are shared across these regimes. And what makes them shared is having a programming model and ideally common libraries that allow us to think about that learning problem or analytics problem as a series of federated aggregations where we can plug in anonymization via DP, the best practices for it for each of those algorithms, where we can provide quantization in the way it intersects with any kinds of SMPC protocols we're using along the way, as pieces of the larger computation that we're trying to run and for the purpose of learning or analytics. You can see the building blocks of these different components in TensorFlow Federated, that there are many pieces that are not yet open source for what Google does today, but the kind of broad structure of libraries for learning and analytics built on a common programming model that can target runtime. So you can see kind of the skeleton of this structure in our open source work, and we'll be open sourcing other aspects of what we do over time. So with that, I'll hand it over to Brendan, who will speak about some of the privacy properties of systems that work this way.
Thanks, Dan. Let me just switch the tabs over here. All right. I think the focus of today's, let me jump ahead. The focus of today's Google Keynote, you can kind of think of as the underpinnings of federated learning and analytics, the bits that are common to both federated approaches, as Dan was sketching out. And I think a nice way to organize some of that material is through the lens of 3 privacy principles that we want to highlight and how we think about building federated learning systems. So the first one of those I want to dive in on is the principle of data minimization. This is about only collecting the data that is needed for a specific computation, limiting access to that data at all stages of processing, processing individuals' data as early as possible, so kind of boiling things down to what you're actually interested in as soon as possible, and then discarding any data you no longer need as soon as possible. So you can think of a lot of this really as just good data handling best practices and good security practices. But this is still kind of the bread and butter of federated computation. So one way to kind of think about this is to compare what we do in the federated setting to centralized computation, which is of course still a completely valid and important way of processing a lot of things. A lot of times it's necessary. But in the centralized computation, which is kind of the light gray on the slide here, you see that not much happens at the client device or in a separate aggregation phase. The typically relatively raw data is collected in the server, which then puts a big obligation on the server to lock that data down and to protect it there. In federated computation, on the other hand, we're trying to push the processing and the aggregation out as far as possible. So a lot of the processing happens on the device, so we can send focused updates. And then we view aggregation as inseparable from collection. And we'll hear in the second or the third part of this talk from Kaylee about some ways we can make our guarantees about aggregation even stronger. To go into a little more detail, I'm going to use this kind of example of cross-device federated learning, but most of what I'm going to say applies to analytics as well. So when you're solving a problem with cross-device federated learning, there's a few stages in that. There's a model engineer that's actually coordinating the development of the model. They're actually probably going to train multiple models, each of which requires a bunch of round trips to client devices during the federated training process. And then finally, that model engineer might look at a bunch of evaluation metrics, pick a good model, and deploy that to all user devices where it can actually make predictions and improve the user's experience. And we found a nice lens to think about privacy in this kind of a setting is to ask what private information might an actor learn with access to different parts of the system. So what could you potentially learn if you could physically access the device or the network or the server itself? And for these 3 questions, data minimization approaches are really the crux of resolving those concerns. So this is why we do encryption at rest and on the wire. Focused updates also minimize these requests because it means we're sending as little as possible on the wire into the server. We're aggregating as early as possible, which limits what you can learn from access to any downstream part of the system and so on. And as I mentioned, we can try to make these, we can make these aggregation guarantees even stronger by bringing in kind of data minimization supporting technologies like secure multi-party computation or trusted execution environments for protecting kind of intermediate state on the server in particular. But data minimization isn't enough. We also need to think about data anonymization. So the principle here is that the final released output of the computation we're doing should not reveal anything unique about an individual. So the aggregate statistics or model parameters that we're eventually going to release to an engineer or deploy to the users of mobile devices, that shouldn't vary significantly based on whether any particular user's data was included in the aggregation. So yeah, what we're talking about here are the things the system actually needs to release, right? Data minimization can kind of protect data in the phases where we don't really want anybody to have access to it. But at some point here, we're going to release models or statistics to the engineer, or we're going to release these models to devices. So that's what the focus of data anonymization is. But before I talk about that, I want to kind of jump back to something Dan was getting at. From the data anonymization lets us kind of think about this from a different perspective. The observation I'm trying to get at with this slide is that both machine learning and data science workflows can be expressed as an iterative process of running queries on data. So training and evaluating models or collecting statistics and metrics. And before we talk about the anonymization of those results, we can note that the interfaces engineers use to interact with that data play a critical role in privacy. And in particular, if the engineer or the data scientist has access to interfaces that allow raw data inspection, it's generally going to be impossible to federate those workflows or to provide strong anonymization guarantees. On the other hand, if model engineers and data analysts use privacy and policy aware APIs to access data that only allows access through aggregates, then the workflows and algorithms on decentralized and centralized data can be the same. And I think this is potentially a really powerful idea that unifies these three federated flavors that Dan was talking about. And it's one of the reasons we're interested in all of them. We'd really like to get to the point where the modeler or the data scientist doesn't really need to care which of these flavors is happening under the hood. They're just comfortable solving their day-to-day work using a set of APIs based on aggregate data processing. So I've kind of said that releasing some form of aggregates for both data science and machine learning is what we want to do, but is that enough? Can aggregated results reveal private information? And I think it will come as a surprise to very few people in this audience that the answer is, of course, yes. And federated analytics is maybe the most trivial example of this, right? We can think of expressing an analytics query as kind of a SQL query here, where we're counting some events broken down by location, age, and timestamp. And if location, age, and timestamp are fine-grained, if you have access to prior information, you might know that the count you see is either going to be 0 or 1. And so knowing which of those worlds you're actually in directly reveals private information. So aggregation is not enough. We need other technologies for data anonymization. Do we have the same problem for ML aggregates? It's maybe less obvious, but again, I think the answer here is clear that at least in some cases, this can be a problem. For other classes of models, it's maybe less clear. Maybe it's not a problem in all cases, but certainly if you have something like a language model and a mobile keyboard that correctly completes the sentence, Barry McMahon's credit card number is, then we have a anonymization problem. So what are we going to do about it? Well, the gold standard is differential privacy. And I'm not going to go into the details of the definition here, but I did want to highlight a couple of things. The intuitive notion of differential privacy is first, for machine learning, as I've kind of expressed things here, your training procedure needs to be randomized. And then we want to make a claim about the output distribution over models. Namely, that distribution over models doesn't change too much when you add or remove all of the training examples associated with any one user. So you want a privacy guarantee that's robust to whether or not a user contributed one training example or 100,000 training examples to the training of a particular model. And this is kind of an important distinction to a lot of research on differential privacy and machine learning, which focuses on example level DP. Example level DP, where you only worry about adding or removing a single training example, can be a really good research test bed, but it's not the kind of privacy guarantee we actually usually want when we're talking about production services. The next point I wanted to make about differential privacy is that we're probably not going to want to claim a single DP number for a full FL system. It's going to make more sense to make different, to provide different guarantees for different parts of the system. And this makes sense because the threat models are very different for different parts of the system. So if we think about kind of threats to the server, hopefully very few people have access to the server, but trying to make it so that somebody with root access to the server only sees DP outputs is a very challenging problem. We can provide stronger kind of central DP guarantees to the, with respect to the model engineer and the data scientist, and we want to provide the strongest guarantees for the models we actually ship out to all user devices, because essentially we want to assume that the entire world will have access to those deployed models. So I want to take a couple of minutes to highlight two really cool advances we've had on providing stronger DP guarantees in the past year. The first is going to apply kind of to central DP guarantees for cross-device FL. So here you can think of central DP basically meaning you still need to take the service provider's word for it that we're running the DP mechanism. But for federated learning, even providing a central DP guarantee is very, very hard. We can't, in general, uniformly sample clients to apply amplification via sampling approaches. We need to make sure we preserve privacy and still ideally make forward training progress, even as the set of devices varies with time arbitrarily. We need a protocol where clients are making local decisions to be efficient and so on. So we've been working on this problem for a while. And with our latest work on practical and private deep learning without sampling or shuffling, we think we have a pretty good solution with the DPFTRL algorithm. And you can see a talk coming up at the 10:20 session from Jung later today in track 1 that will dive more into the details of this algorithm. But as I said, ideally we would want to go even farther and provide a DP guarantee even to the server itself, so that we would have the DP protection even if somebody had access to the internals of the server. And we can think of that by basically saying, the goal here is to use crypto or trusted execution environments so that the server only sees those DP outputs. And we have a couple of approaches to that problem based on the distributed discrete Gaussian mechanism and the Skalam mechanism. And I definitely don't have time to go into all of the details on this slide, but we will have a poster from Ken Liu on this later in the workshop. Excuse me, I raced my bike yesterday and my throat's a little hoarse. So the third privacy principle I wanted to mention is in some ways the most important or should be the foundation of the other ones, and that's around transparency, consent, and verifiability. Users of products and services need to understand and approve of the ways in which their data is going to be used. And when we're making data minimization and anonymization claims, we'd really like those to be verifiable by users and policymakers. Data minimization and data anonymization are kind of directly driven by technology and algorithms, which is why we've kind of focused a lot on those. But in an end-to-end system, there's important technologies that can apply to verifiability as well. And we've taken some big steps forward with this with Android 12. There was a couple of announcements associated with this that I think are pretty exciting. The first is the introduction of Private Compute Core, which is an open source kind of secure environment inside the Android OS that's going to be the home for many new privacy-sensitive features. So that's already powering features like live caption, now playing, and smart reply. And one of the key kind of security properties of code that runs inside the private compute core is that it doesn't get any direct network access. But of course, going back to kind of Dan's intro, we still want to benefit from the ability, from the data that private compute core has access to in order to improve those products and services. And that's where federated learning and analytics comes in. So private compute core can talk to private compute services, which will provide FL and FA. And we've committed in the blog post referenced here to open sourcing that code as well. So there's a lot more to do here, including making verifiable differential privacy claims, making sure clients can verify what code is actually running in the real services and so on. But I think this is an important first step of establishing the infrastructure that will let us make stronger claims about verifiability of the other approaches we're taking. And with that, I'll hand it over to Kallista, who's going to talk more about some of the technologies we can use to strengthen our guarantees around aggregation.
All right, great. It's a pleasure to be talking with you today. So as Brendan mentioned, one of the key features of being able to enable strong verifiability for our customers, to be able to enable things like distributed differential privacy, where the first values that become visible to our servers are already differentially private. Both of these are really touching on aspects of how do we limit the amount of faith we have to put in parts of the system by distributing trust among multiple actors, making it as hard as possible for accidentally or otherwise for anything other than the expected data flows to be possible. And so there's a few different ways we can go about approaching these problems, these distributed trust problems. One of those ways is to find a completely trusted third party and just delegate trust to them. If you had such a third party, you could rely on them to do things like shuffling or aggregation without either the clients or the rest of the federated learning system being requiring faith in those players to play their parts as expected. But unfortunately, it's very hard to find these trusted third parties in practice. So we often turn to more technical solutions. One big area of technical solution that has been growing in interest recently has been trusted execution environments, basically using specialized hardware which limits what can be done either by even by the folks who own and operate this particular hardware. And I'm going to talk a little bit more about that later in this part of the talk. But first, I want to touch base more on what we can do with pure cryptography without requiring any special sorts of hardware. In this setting, we can think about the problem that's kind of core of, say, distributed differential privacy, this aggregation problem, which is how do you take the setting where each of the users has some one or more tensors, vectors that they want to contribute to the server, compute the sum of those such that the server only gets to see the sum. This is something we've been working on for quite a while. Back in 2017, we published some work that showed that it is, in fact, quite possible to do this in a communication efficient way that's also robust to clients going offline. And just to refresh you on the kind of the high level of how that works, the basic setup that we do is we can have pairs of users cooperatively sample a random vector that's the same size as the inputs they're trying to contribute. Then one user takes the positive version of that vector, one person takes the negative version of that vector such that those matched pairs sum to zero, kind of like antiparticles colliding and annihilating one another. So we have each pair of users do that. And then when the user goes to contribute their own value, they add their half of each pair that they cooperatively sampled onto their personal update. so that what arrives at the server from each user is completely masked. From a cryptographic standpoint, it looks indistinguishable from randomness. But when the server adds all of these updates together, and only when it adds all of the updates together, do those masks cancel out, allowing the server to compute the sum that it was actually interested in. Now, there's some additional bells and whistles that are required to make this work very efficiently and to be able to recover safely from some set of the users dropping out during the execution of this protocol. But it is possible to do that and produce a protocol that runs efficiently for up to about 1,000 users at a time. So that's where we were in 2017. In 2019, we published about how we're using this as part of our federated learning systems at Google. In 2020, we also published about how we're using this to power our federated analytics systems. But one of the things we've discovered as time's gone on is that this limit of about 1,000 users is good, but there are a number of applications, especially when we start digging deeper into distributed differential privacy, especially when we start going after learning and analytics problems that cover, say, billions of users, like in a very widely used application. There's a lot of value that could come from larger cohorts of users at a time. And the core problem with scaling up beyond about 1,000 users is, I mentioned that each pair of users has to do something in that application, in that algorithm earlier. So every pair of users has a set of work to do, which means that the amount of work happening in this system was growing with n squared, if n is the number of users. In 2020, we published an extension to the secure aggregation algorithm, which shows that actually you can retain all of the same privacy properties using a much sparser communication graph. Actually, each user only needs to establish these pairwise masks and other secrets with a logarithmic number of other users. And you can show that with extremely high probability, like it's more likely that your core cryptography will break down than that this choice will break down. You can show that all of the same privacy and security properties will hold if you just randomly assign users in this much more lightly connected graph. You can do the analytics, and basically what you show is you replace these n squared factors with approximately n log n factors. But really the core outcome of this is if you wanted to consider doing like an aggregation over up to 1 billion users, you could use the old protocol with a privacy unit of 1,000 users and just do that 1 million times. Or you could use the new protocol once over the entire 1 billion users, having that as your privacy unit. And it actually turns out that that single application of 1 billion users would be computationally and communication-wise cheaper than the million executions of the old protocol at the weaker privacy unit. Another way that we're looking at scaling out the reach of our privacy-preserving protocols is thinking about how do we take federation to larger, sparser models. So one of the places where you find these large, sparse models showing up is when you start looking at learning problems that have to do with training embedding-based models. So things like training a word-based natural language model or training a compound model where you have multiple copies of the same model, one for each subset or cluster of users. Or in a lot of cases in federated analytics, you have sparsity problems where an individual user only can contribute to a small component of a query, say a small, or one or a few bins of a large histogram. These sparsity problems show up a lot. And the more we can handle the sparse domains, the more fine-grained queries we can execute efficiently. When we start dealing with sparsity, there's kind of two places where this shows up in our federated learning systems. There is the sparse aggregation problem, which is the kind of natural extension to private aggregation that I was talking about earlier. But especially in the federated learning setting, there's an analog, which is about sparse model download. So if a device only has information that's relevant to a small portion of the model, you might want that device to download just the portion of the model that it's going to update, compute an update on that portion, and then do a sparse update of just that portion of the model. Of course, which portion of the model the device is trying to update is probably also privacy sensitive since it's based on that device's data. So we really want private versions of both of these protocols. I want to give you just a flavor of some of the ways you can go after these privacy preserving sparse protocols. There's a number of different approaches here that are being explored kind of in parallel, and partially it depends exactly on what sparsity patterns your particular problem has in it. So one thing you might imagine doing to approach that private retrieval problem is using an idea called private information retrieval. And the basic idea here is using homomorphic cryptography, you can actually do some kinds of math without decrypting the data that you're working over. So you could imagine having a server which has a set of files where each file is, say, a slice of the model that could be trained, and consider that as a vector. And you could have a device which expresses a query as a binary vector that has a 1 corresponding to the file that it's trying to download from the server. If the device encrypts the elements of that query using a homomorphic crypto system, we can then have an encrypted vector that the device uploads, and the server can do an inner product, a dot product of that encrypted vector with its data vector without doing any decryption, and produce, and the result of that is going to be an encryption of only the file the device is interested in. That can then be sent back to the user's device, decrypted using keys that only the device has, in order to complete this private retrieval protocol, where the server learns nothing about which file was downloaded. We've been working to integrate some of the ideas that you would need to support private retrieval into TensorFlow Federated. If you're interested, you can look up the tutorials in TensorFlow Federated on Federated Select, which embodies the same pattern that I just described here. On the sparse aggregation side of things, you could look to develop custom protocols, or you could, another approach that you might use here is to reduce sparse aggregation, say sparse histogramming, to things we already know how to do. So for a flavor of how that might work, you could imagine taking the sparse histogramming problem and reducing it to a sparse shuffling problem by having each device say, I have a message and my message says increment histogram bin number 54,732, for example. And then if you were able to shuffle those messages together, what you'd end up with is essentially a representation of a histogram composed out of increments to various bins without being able to tie those increments to the source. You could then try to look for ways to reduce sparse shuffling to things we already know how to do, like dense secure aggregation. And one of the technologies we've been exploring for that is IBLTs, which are kind of a combination of Bloom filters with hash maps. The basic idea about how this might work is you can imagine a large vector with message-sized slots, where messages are like the kinds of things that I was talking about before. And each device is going to choose a random slot to put their message in. As long as no two devices randomly choose the same slot, you get a shuffle of what you're looking for. Unfortunately, because of the birthday paradox, even with a rather large vector, if you follow this approach naively, it's highly likely that at least some of the slots are going to be conflicted and you're going to lose some data. But it turns out you can do something slightly more clever. Rather than just putting the message in a random slot, what we're going to do is have devices choose a pseudonym for themselves, take k hashes of that pseudonym using well-known hash functions, and use those hashed pseudonym values to decide which slots to put their message in. When they put a message in a slot, they'll put both the pseudonym and the message there. Now when the server goes to decode this vector, the server can look at any slots that happen to be unconflicted, and recover both the message and the pseudonym. With the pseudonym in hand, it can compute all the slots that message should have been in, and using the same hashing strategy that the devices use, remove those messages from those slots, subtract them off, and that will have produce further slots that are now newly non-conflicting. And you can repeat that process basically peeling off the messages until you've recovered all of the messages in the data structure. And kind of the surprising thing here is with a vector length about 1.3 times the number of messages that you're trying to transmit, there's extremely high probability that you'll recover all of the messages in this system. Now, for the last little bit, I want to return to trusted execution environments. Cryptography is a wonderful way to approach this problem, but increasingly trusted execution environments are coming online, and they provide some very appealing properties in terms of the flexibility and the communication efficiency that you can obtain when you have this kind of specialized hardware available. So what does it take to really bring trusted aggregation or trusted retrieval online? Well, the first thing you need is production scale access to enclaves, to the hardware that provides these specialized properties. Specifically, the properties we're interested in are measurement, being able to have hardware that can provide cryptographic guarantees about what is running inside that hardware, what is the process that's running, to secrecy, to promises that what is running inside this enclave is not available not visible to anybody else, including the root or owner, hardware owner, and integrity, that root hardware owner is also unable to influence what's happening inside of this hardware. And you really need all three of these properties to be fully in place in order to achieve the kinds of goals that we're after. The second thing you need is a way to connect the execution that's happening in that hardware to the intended behavior. Part of that is what I mentioned before, this enclave measurement. That really only lets you connect what is executing to a hash of a binary. There's a lot of gap in between the hash of a binary and the intended behavior. Really, you need an entire ecosystem that allows you to say, connect the hash of the binary to the specific binary that's running in a verifiable way and show that that binary is really available for view to everybody. So verifiable append-only ledgers end up being extremely important here. You need a reproducible build system so that you can reliably connect code, say in an open source repository, to binaries that are being executed in a way that is verifiable by end users. You need the code to be auditable, say open sourced, and you also need to be able to prove properties of the code that you're interested in. So it's not enough to just run any code in these enclaves. Often you need to specially structure your code so that it's oblivious, for example, so that memory access patterns are non-informative. And you might even want to provide a formal verification or proofs that your code is, in fact, embodying the privacy and security guarantees that are important. Finally, you need to build all of this into a distributed system with all of the usual distributed goals, like high throughput, low latency, robustness, without disrupting any of the above properties, which can be quite challenging when you start thinking about things like, how do I build a distributed private aggregation system that releases at most one sum, while also processing the data faster than any single enclave can handle, while also accumulating data for a longer period of time than the average uptime of a production enclave, et.cetera. Finally, I just want to call back to the centrality of transparency and verifiability, like was mentioned earlier in the talk. Things like the private compute core and private compute services are some of the investments we've been putting forward in this area to really increase the ability for devices and owners of those devices to really be able to verify and provide the opening for verification of what is running as their data is being processed, including all the technologies we've been talking about so far. And with that, I think we are on to Q&A.
Thank you, Kallista, Dan, and Brendan. And if you have any questions, please feel free to either drop them in the chat box or unmute yourself and ask your question directly to one of our speakers. There's already a question in the chat box. Maybe we can do that very quickly. The question is from an unknown person. Pretty cool. The question is, in your opinion, what is the most compelling reason or reasons to do FL? Is it to preserve the privacy of users, to scale, reducing the infrastructure costs, to support diverse clients, periodically disconnected mode of operation, or something else altogether? Who wants to take this question?
I'm happy to quick pass. I think the main reason that we are interested in this is this feedback loop between, giving users better privacy is good for Google. It's good for the app. It's good for Google's apps and services, and it also enables them to be better. So that's the main goal. It's privacy and the improvements to Google's apps and services that better privacy can enable. The scalability question, I think it doesn't really help there, or at least we haven't even, nobody's even asked us to try to make the case on those terms. I don't think it would pencil out super well. I think the diverse clients, for example, I think that's a consequence of the first. Like, we want to be able to hear from all devices because that gives us the most representative data, which enables the apps and services to be the best, and that Google can build. So I think it's the feedback loop between privacy and utility that is the most motivating.
Thanks, Dan. Elaine has a question. Elaine, do you want to unmute yourself and ask the question directly?
Yeah, I have a question for Kallista Kelly. I guess we are interested in the sparse aggregation problem. And do you have any applications? I guess it would be nice to see how these techniques are going to be used in action in the actual machine learning application. So if there's any pointer to the application, that would be very helpful.
Yeah, I'll have to look at what we've published in terms of pointers in written form. I can say that there's at least two that I find very interesting. One is on the federated analytics domain, where you can imagine large histograms of various sorts, either because they're multidimensional or just because the underlying domain is either actually an open set or something similar to an open set, where you're trying to say, find the most popular songs or most popular words in a corpus or something like that. So there's that analytics side of things. The other side that I think is really interesting is on the federated learning side, where for a variety of reasons you may want to be contributing to a block of parameters in a much larger model. And kind of the key distinguishing factor here is is a device contributing to essentially a few scalars, or is it contributing to a much larger block? And so there's a number of places where that kind of much larger block shows up. Sometimes for the underlying model, it's just that there's you're training a collection of models where, say, there's one for each music genre or one for each natural language that could be spoken or something like that. But there's also some places where your training algorithm, in fact, if you're trying to train a larger model than is comfortable to be just shipping the entire model to device, then you might say, take a random subset of the parameters in that model, send that to device, and send a different set to a bunch of different devices. So that could be yet another different application where private aggregation is interesting. You want to be able to produce one aggregate across a large number of users, but it has a very different flavor. I guess we're kind of looking, there's two different axes of sparsity that are really interesting here, which is one is how sparse are the inputs, and one is how sparse is the aggregate that you're computing. And so different techniques that we've looked at tend to be, have very different efficiency properties depending on which of those things are sparse. For example, the IBLT's version that I talked about is great if the outputs are sparse. If the outputs become dense, that algorithm actually isn't a great idea. It's better just to do dense aggregation in the first place. So hopefully that gave you a bit of a flavor, but I agree that it would be valuable to have more concrete, these are specific applications that could be of interest.
I guess I also have a question about, you mentioned the sparse model download, and you said the device wants to download a small portion of the model it cares about. But then you also mentioned the device will be updating part of that model. I guess I don't fully understand what the threat model is. For instance, can the server see that the client has updated this part of the model and infer that this is the part I'm interested in just based on which part has been updated?
So the goal would be to combine the private download with the private upload. So what the server would see is the aggregate of all of the sparse updates across all of the devices in the population. And you can layer different, the ideal goal would be to use distributed differential privacy such that the server sees only a differentially private version of that. So if you do that properly, it should be indistinguishable from, basically you shouldn't be able to tell either which device uploaded to which part of the model. You can do that without distributed differential privacy. But even with, once you add distributed differential privacy on, you shouldn't even be able to say like with any strong confidence that any part of the model was or was not updated by some device in the system.
Mm-hmm.
Thank you, Elaine, for the question. So I have a quick question for Brendan. There's a lot of DP and privacy experts on the call. So if you were to ask academic researchers to work on one challenging problem for federated learning, do you have something in mind?
Oh, that's a great question. Actually, just jumping back to the previous question, I wanted to add one thing. We have a tutorial up on the TensorFlow Federated tutorials page that looks exactly at some of these examples, combining kind of federated select for sparse download and a non-private sparse aggregation. So you can, it just shows how this applies to things like a logistic regression, where you have maybe a very large number of binary features, but they're highly sparse, and so each device only cares about a small subset of those binary features, and so only needs to download and then upload the smallest, the subset that occur on that device. So that's a very concrete example if people are interested in looking at that. I don't know if I could pick, to Peter's question, just one problem. I think I'm excited to see work that's targeted at any of those kind of core challenges. I mean, the big ones I see are still on, going farther on the distributed differential privacy front. And also, how do you kind of simultaneously get good distributed differential privacy guarantees and good central DP guarantees? We're really excited about the DP FTRL algorithm, but we don't know how to combine that, say, with secure aggregation. We could potentially make it more distributed by using trusted execution environments, but it just kind of requires more complex processing on the server. I guess I'll throw out one other open question, I think, or research direction more than concrete question, I think is really important. That's how do we make differentially private machine learning easier to do in practice? It's one thing to kind of produce an algorithm and show that there exist hyperparameters and settings and data set sizes where it works. It's a big step from there to giving something to ML practitioners that's really easy to use, where they can just kind of flip a switch and provide maybe a little bit of input on what kind of privacy versus accuracy trade-offs they want, and then have it just work. So kind of self-tuning, auto-tuning algorithms, I think, is a really big challenge for federated learning in general, and federated learning with differential privacy in particular.
Thanks a lot, Brendan. Okay, so we're going to take a 5-minute break, and we're going to resume at 9:55 a.m. Pacific time, and we have a talk by Professor Martin Yagi. So please make sure to be back at 9:55. Use this break however you want. If you want to join Gather Town and walk around, talk to people, please do that.